Hello, welcome to this lecture on process control, chapter 3, part 2, first order systems. So we are going to see about thermometer and its transfer function. In the last lecture, I told you we were discussing first order transfer function general form, and then I gave thermometer as an example, most common example of first order system. So it will have a transfer function of the form k by tau s plus 1. So in this lecture and next lectures, we will be deriving the transfer function of thermometer and show that it is of the form k by tau s plus 1. So let us consider the thermometer here, which is kept in a bath. The liquid temperature, this is a liquid bath. Its temperature is, let's say, Xs, and thermometer reading is Ys. So the liquid side temperature is shown as X, and the thermometer reading is shown as Y. So Xs and Ys are steady state temperatures. X is for input, that is liquid temperature, and Ys is the thermometer reading at steady state. The bath has been at steady state for a long time, so bath temperature is no change, constant X is, so thermometer reading also constant Ys. Now let us say at T equal to 0 onwards. T equal to 0 onwards, that is T greater than 0, the liquid temperature here, bath temperature, begins to change as a function of time. Begins to change as a function of time. Xt, X bracket T, X varying with time. I simply call X. Now the bath thermometer reading also will vary as a function of time, Y of T or Y. So at unsteady state, T greater than 0 onwards, because of some disturbance, the bath temperature begins to change as X. Accordingly, the thermometer reading also will vary as a function of time Y. So these are at unsteady state. So unsteady state is T greater than 0. Steady state is T less than 0. So T less than 0 represents steady state and T greater than 0 represents unsteady state. Now the transfer function relating Y and X, transfer function relating the Y and X. X is the input for the thermometer and Y is the output for the thermometer. Output variable of thermometer is Y, input variable for the thermometer is X. The transfer function relating these two variables will be first order and will, as we are going to derive. Okay. Now this involves certain assumptions. What are the assumptions? Now all the resistance to heat transfer is in the film surrounding the glass bulb of the thermometer. So where is if you see the glass bulb, where does the heat transfer take place? The heat transfer takes place from the bath to the bulb. So if you see a cross section of this bulb here, I've shown it magnified here. So this is the glass bulb. Inside you have mercury. The liquid, thermometer liquid is inside here. Mercury surrounded by glass bulb. The heat transfer from the bath to the mercury. Heat transfer there is a resistance for heat transfer, and this assumption says all the resistance, complete resistance for heat transfer, complete resistance to heat transfer is in the film surrounding the glass bulb. This is a film. Imagine a film. There's a thin film of liquid, thin liquid film surrounding the glass bulb here. And all the resistance for heat transfer is in the film. There is no resistance. There is no resistance there is no resistance in the glass and mercury. There is no resistance in the glass and in the mercury. Or in other words, you can say there is negligible resistance in the glass and mercury. Theoretically, no resistance. Well, this is the first assumption. Second, heat transfer has Heat transfer has resistance as well as capacitance. So capacitance, where is this capacitance? The thermal capacity is in the mercury. The thermal capacity is in the mercury. All the capacitance for heat transfer is in the mercury here. It absorbs all the heat. The mercury absorbs all the heat because it has got all the thermal capacity. Not the words all in both cases. First case is also entire resistance. Second case also all the entire thermal capacity. Entire thermal capacity for this heat transfer is in the mercury and it absorbs all the heat which is coming from the bath. At any instant, it attains uniform temperature throughout. That is, throughout means the entire length of the mercury column in the thermometer attains uniform temperature throughout. Heat transfer takes place here, mercury absorbs heat here, and at any instant, it's the same temperature throughout. If it is Y here, throughout Y. So the second assumption. Third assumption, the glass wall does not expand or contract. This is the glass bulb. Sorry, this is the glass bulb. It does not expand or contract. This is the result of consequence of these first two assumptions. Glass bulb as concerned, it is sort of inert to the heat transfer. The glass bulb is an inert for the heat transfer. It remains inert, so no resistance, neither resistance nor capacitance. So glass bulb neither expands nor contracts. So these are the three assumptions based on which the transfer function of thermometer will be derived. The transfer function which is going to be derived will be subject to these conditions, these assumptions. So how will you derive this? You have to know what is the process taking place in this system. What is the process taking place? The heat transfer from the bath to the thermometer. So you have to know how to write the heat transfer equation. So if you write the heat transfer equation, from that we'll be able to derive the transfer function. So that will be continued.